1314 and Math 1324, presented by Yvette Chuca, Ruben Carrizales, and Albert Isasi. This session will be recorded so that you may come back to it at a later time, and also for those who may have missed today's presentation may be able to watch it at a more convenient time. Thank you. So now at this time, please mute your mics for best sound experience. We don't want any feedback interfering with today's important lesson. Without further ado, here is Mr. Ruben Carrizales.
Oh, hello everyone. Thank you for joining us this Friday, Groundhog Day, for our Happy Math Hour. So for today's Happy Math Hour, we're going to go ahead and cover evaluating combination of functions and composite functions. Okay, so let's go ahead and get started. All right, so combinations of functions. So the best way that I like to talk about composite functions is a composite function is just a regular function, but instead of just putting a single value, what you're going to be doing is putting another value. Now, the way you see it here on this first page is the way the syntax has for your book on the computer. But I like to rewrite this because on this first one, A, it says F plus G. So on these particular ones, sorry, we're doing order of operations, just basic mathematics. So what this is saying is that I want to add function F with function G. So I'll rewrite it in this format, F of X plus G of X. And by having it this way, I can just substitute what F of X and G of X are, okay? So if I do this, F of X is the 3x minus 7 plus G of X, which is 4 minus X, and then all I have to do is simplify. Simplify means just combining my like terms. So I have a 3x and a minus x, that's going to give me a 2x, and the minus 7 plus 4, that's going to give me my negative 3. So the addition of f plus g means just the addition of these two functions. My outcome is 2x minus 3, okay? So very, very similarly, if I want to subtract these two functions again, the syntax on your book has it like this. It says f minus g of x. So I like to rewrite it in what I'm really doing. This problem is asking me to subtract function f of x with g of x. So having it in this format, all I have to do is just substitute and simplify once again. So again, f of x is 3x minus 7 minus g of x. Now, if you notice, I had to put a parentheses on my two terms here because of the subtraction. This subtraction has to be distributed to all of the terms from the second function. So before I can simplify, the first thing that I need to do is I need to distribute that negative symbol, okay, or the subtraction. So a negative times a positive 4 is going to give me a negative 4. A negative times a negative x is going to give me that positive x. So now I can combine my like terms again. I have two terms that have a single x, so 3x plus x is 4x. And the minus 7 with a minus 4, since they're the same sign, I'm going to add these two values. 7 plus 4 gives me the negative 11, okay? And then we have this next example. This C is basically wanting us to multiply f with function g. And if you recall, when two things are next to each other, we don't have to put the symbol that is a multiplication. We know that f and g are being multiplied. So I like to rewrite it again, just like before. Since it's asking me to multiply, I like to rewrite it as f of x times g of x, okay? Then I just do substitution again. F of x is 3x minus 7. G of x is 4 minus x. And if you notice on this particular one, now I had to put parentheses on both because in order for me to simplify, I have to apply FOIL, meaning that this first term has to be multiplied with both of the terms of the other function, and the negative 7 also has to be multiplied with all of the terms of the other function. So when we do that, we have 3x times 4 is a 12x. 3x times a minus x is a minus 3x squared. And then the negative 7. Negative 7 times 4 is a negative 28. And the negative 7 times a negative x is a positive 7x. So now we can combine our like terms, and we do have two terms that are equal. We have a 12x and a 7x. Not equal, but similar, right? So when I combine those two terms, I get minus 3x to the second power plus 19x minus 28. Now, keep in mind when you're answering these on the computer or in your class, the order doesn't matter, okay? But for us, there's a standard way to write our polynomials, and we always like to write them in descending order, meaning the highest exponent goes first, and so on and so forth. But again, when putting them in the computer, it doesn't matter. The computer, as long as you have the right values, is going to take the answers. Okay. Now, the last example here on just basic operations of functions, we have f divided by g of x. So what this is saying is just, again, I want to divide function f with function g, so I will write it just that way. This is telling me that all they want is f of x divided by g of x. I will substitute once more. So here, f of x is 3x minus 7, g of x is 4 minus x, and then I would simplify, or if I can factor, but on these two, on this result, there's nothing that I can factor from either the numerator or denominator, so this is my answer. Excuse me. So your homework is going to ask you an additional question when doing these basic math operations for functions. And they're going to ask us to find the domain of the D part. And the reason why they're asking us to find the domain of this one is because our result ended up as a fraction. And as you recall, when we're dealing with fractions, we never want a zero on the denominator. So if that happens, then what we have is a restriction on our domain. There's a x value that I cannot use for this function. If not, I get an error. So that's what it's asking us. What is the domain of this function? And again, if we don't see it, if we don't see what value we can put for x here that will give us 0, well, then you can solve it algebraically. Set 4 minus x equal to 0, and you see that if you solve for x, the value that you cannot put in here is 4. If I put 4 for x, 4 minus 4 is going to give me 0, hence it's going to give me an error. So in English, the domain for this result is all real numbers except for 4. Now, I believe in the computer, it's going to ask us for the interval notation of this. So the way that I would write this in interval notation, again, we read graphs from left to right, and it would be from negative infinity. Oh, and then missing a comma here, so let me just put it here. There should be a comma between the negative infinity and 4. And then, and let's talk about the syntax here, okay? Again, and I think we've covered this already, but the infinity symbol always has a parentheses. Since I want to stop at 4 but not use 4, this also is a parentheses. Then we have this U-looking shape. This means union or and, so this is and. The other part, starting from 4, not including 4, all the way up to positive infinity, okay? So you'll be asked for the domain when dealing with the division of two functions. So let's go ahead and look at this next set of examples. And again, we're doing basic operations. We're going to be doing adding these two functions, subtracting the two functions, multiplying the two functions, and dividing the two functions. So let's get started. Let's start with the first one. Again, I like to separate it or do what it's actually me to do. F plus g of x wants me to add f of x with g of x. Then all I have to do is substitute. F of x is x squared, g of x is the 2x minus 5, and simplify. Simplify means if I can combine like terms. Unfortunately, on this problem, all three terms are different terms, so there's nothing that I can simplify, so that's going to be my answer. X squared plus 2x minus 5. All right, let's do the next one, the subtraction. Oh, so there it is. So let's do the next one, the subtraction. So again, rewrite this as f of x minus g of x and substitute each one. So we have f of x is x squared minus g of x. And if you noticed again, I put up parentheses because I have two terms that are being subtracted. So before I simplify, I need to distribute that sign. So a negative times a 2x is a minus 2x. A negative times a negative 5 is a positive 5. And then again, none of these terms are like terms, so there's nothing to simplify or put together. So the answer of the subtraction of these two functions is just x squared minus 2x plus 5. And again, the order doesn't matter. Okay. So let's do C. And this is the product of function f with function g. Rewriting it as f of x times g of x. Do our substitution, x squared times 2x minus 5. And on this simplifying one, I just need to distribute the x squared, right? So the x squared times the 2x is going to give me a 2x to the third power. And then x squared to the minus 5 is going to give me a minus 5x squared. And this will be my answer for the product of these two functions, 2x cubed minus 5x squared. Okay. And then the last one, the division, right? So we want to divide f of x with g of x. Let's go ahead and substitute. So if we substitute, f of x is x squared, g of x is 2x minus 5, and simplify. So again, similar with this one, there's nothing for us to simplify. Cannot factor anything that will make something cancel from the numerator and the denominator. So that is going to be my answer. My answer is going to be x to the second power over 2x minus 5. But then again, your homework is going to ask us to find what is the domain of this function. Is there a restriction or is there an x value that I cannot use? So, and similarly, if we don't see it, all you have to do is set the denominator equal to 0, 2x minus 5, and solve. So when we solve for x, we see that if I put the value 5 halves, this will give me a 0 on the denominator. So in English, the domain is all real numbers except for when we use 5 divided by 2. Okay, so in interval notation, again, interval notation is from negative infinity to 5 halves, union from 5 halves to positive infinity. Okay, and these do have to be in order because again, we read left and right, so we have to start from the farthest left to the right. Okay. All right, let's do this example. Um, we have function f of x, which is x squared plus 3. G of x is the square root of 2x minus x. So let's go ahead and do f plus g of x. So again, what they want me to do is f of x plus g of x. Let's go ahead and substitute. So f of x is x squared plus 3. G of x is the square root of 2 minus x, and simplify. Well, this is it. There's nothing else that we can simplify, so this would be my answer. It just stays like that. Again, I did a little rearranging here of the values just because I like how the constant always to the end, but you don't have to. Again, this is just my format. As long as your values are correct, the order does not matter. Okay. All right, let's do the next one. F minus g of x. Okay, so let's do our substitution. F of x, x squared plus 3, minus parentheses, the square root of 2x minus x. So before I simplify, I need to do that distribution of that negative symbol, and then it just applies to the square root. Okay, it does not go inside, it just stays outside. So it's x squared plus 3 minus the square root of 2x minus x. This will be my answer once again. And you don't have to rearrange it, okay? Just any order will be fine. And then let's do C, the product of these two functions. So let's go ahead and do it. So on this one, we want to multiply x squared plus 3 times the square root of 2 minus x. This one, you can think of it as distributing the square root of 2 minus x to both of these terms, or just taking the x squared and the 3 and multiplying to the square root of 2 minus x. So if we do this, again, we have this. I want to write it so you can see it. So when we do it, actually, it looks like the computer will take this answer. You don't have to have, and it wouldn't mark it wrong if you have x squared times the square root of 2 minus x plus 3 times the square root of 2 minus x. It will take it, but it looks like if you just leave it like that, the computer's going to be okay with it. You don't have to multiply. So then let's do the last example, f divided by g of x. So again, f of x is x squared plus 3. My g of x is the square root of 2 minus x. Again, similarly, we don't have anything that can be simplified, so that is our answer. Okay. So again, once again, is there a restriction on our domain? Is there a value that we cannot use that will give us a 0 on the bottom? And there's two ways to solving or to find out if there's an x value that we can use or that we can put in that gives us a 0 on the bottom. So one way is by using our square root property or square or inverse property, right? To get rid of the square root, we take the square on both sides. So 0 squared is 0, and the square root with a square. I know our students like to say they cancel, but basically it becomes a one value exponent, which gives us just the 2 minus x. Then I just subtract 2 on both sides, multiply it by a negative on both sides, and then here I have 2 is equal to x. Okay, now keep in mind that when we do take the square root, okay, we're always ending with two values, right? So here on our interval notation, the way I like to tell my students is you start with what gives you 0. Okay, so I know that if you put 2 for x here, 2 minus 2 gives me 0, and the square root of 0 is just 0. Hence, I'm going to get an error. I cannot use 0. Now, are the values that I'm going to use that I can use, are they to the right of 2 or are they to the left of 2? So then I say to myself, okay, if it's to the right of 2, so if I put um, 3 here, 2 minus 3 is going to give me a negative value. So 2 minus 3 is going to give me a negative 1. Hence, it's going to be an imaginary number which doesn't exist. So hence, I cannot use the values to the right of 2. But just so we can check, what about to the left of 2? The left of 2 would be a 1. 2 minus 1 is just 1, and the square root of 1 is 1. So we do get an answer. So the values that we can use are to the left of 2. So then my interval notation is going to be to the values to the left of 2 in this notion, from negative infinity all the way up to 2. And again, I have to use parentheses because that means that I stop at 2, but I'm not including 2. Okay? All right. Now let's move to something a little bit more interesting too, which is called composite functions. This is when I was talking to you at the beginning. Okay, composite functions is the notation is given by these, and what this is just saying is that given two functions, depending on what the first function or name is, that's the one that goes first. So for instance, I have this function f of x is equal to x plus 4 and g of x is equal to x minus 3. If I want to do the first one here, f composed of g, what this is really saying is that I want to put function f, because f comes first, to function f, I'm going to put function g. So instead of putting the value, does anyone have a question? Please let me know. If you have a questions, put it on the chat or go ahead and unmute yourself, okay? All right. So what this is saying is that instead of putting in the value to the function, I'm going to put in another function. So, and then I just have to do substitution, just like I was doing the basic operations with functions. So again, what I do here is I write the function that's inside that I want to plug in, which is the x minus 3. So this x minus 3 has to be validated to the function f. So function f is the x plus 4. So here I have x minus 3 plus 4. So here I replace the x with a g of x, right? So x minus 3 plus 4, now I have to simplify. I have a negative 3 plus 4 is going to give me a positive 1. So the composite of f of g is x plus 1. Okay? So let's practice some more. Okay. If you see on this one B, now we switch the order. Now this problem is saying G composed of F, or F, G the composite of F. Okay, so I like to rewrite it in this format. G, and to function G, I'm going to put in function f of x. Okay, so first I substitute what f of x is, since f of x now goes inside, and f of x is x plus 4. So now I'm going to evaluate. Everywhere I see x for my function g, I'm going to plug in the x plus 4. So then we have x plus 4 minus 3. So now I simplify again, and I have x plus 1. Now I do want to word of caution, okay? Um, the f dot g and the g dot f, we got the same answer for both of these, but this rarely happens. It's actually, it doesn't really happen. It just happened this time on the example that we got, that it ended up to have the same answer, but this normally never happens. Okay, you will know. So don't think that you get the same answers all the time. Okay, this was a once in a lifetime um, chance that we had the same answer. Okay, all right. So one of the questions I always get is on these is like, what do we do on this one? G composed of G. Well, this one's easy. All this is asking is that for function G, we're gonna put itself in. Okay. So again, function G is x minus 3, and everywhere I see x for the function G, I'm gonna plug in that x minus 3. So then we have x minus 3 minus 3. Simplify by combining my like terms. So minus 3 with a minus 3 is a minus 6. So G composed of G, or the composite of G and G, is x minus 6. Okay, let's see. Let's do some more examples. Um, what if we have these two functions, x squared and g of x is equal to x minus 2. So let's go ahead and do the first one. F composed of G again. F comes first, so to the function f, I'm going to put in function g of x. So I replace g of x what it is. It's x minus 2. Now I'm going to evaluate. Everywhere I see x for the function f, I'm going to plug in this value, x minus 2. So we have this, x minus 2 squared. So we're going to simplify. X minus 2 to the second power is like having 2x minus 2's. And then we can go ahead and do FOIL. X times x is x squared. X times a minus 2 is a minus 2x. Minus 2 times x is a minus 2x. And a minus 2 with a minus 2 is a positive 4. Combine my like terms, I have 2 minus 2x, which is going to give me the answer. F composed of G is x squared minus 4x plus 4. Okay? All right. We're doing good. So G composed of F. Now we switch the letters, right? The variables or the names. So now we want to evaluate function G composed of f of x. So f of x goes inside, replace f of x with what it is. F of x is x squared. So I take function G, and everywhere I see x, I'm going to plug in this x squared. So when I do that, I have x squared minus 2. It says simplify, but there's nothing to simplify, so this will be my answer. G composed of f equals x squared minus 2. Okay, easy stuff, I hope. So let's do uh, G composed of G, G composed of itself, right? So this is the notation or the syntax that we evaluate this. So for function G, we're going to put in function G. So let's go ahead and replace what function G of x is inside. We have x minus 2. So now we're going to evaluate. Everywhere I see x for function G, I'm going to plug in this x minus 2. So when I do this, I have x minus 2 minus 2. Combine my like terms. Minus 2 is a minus 4. So G composed of G equals x minus 4. Okay, and hopefully you see that we're getting an equation. It's not a single value. Okay, so just keep in mind on these. All right, so let's do some more examples, and then we'll practice finding the domain of the functions. So let's do f composed of g for these two functions. F of x is the square root of x plus 4. G of x is equal to x squared. Okay, so let's do f composed of g. So f composed of g again, it's f of g of x. Replace g of x with what it is. G of x is x to the second power. So everywhere I see x for function f, I'm going to plug in the x to the second power. So this is going to be the square root of x to the second power plus 4. Okay. Um, And there's nothing for me to simplify, so this will be my answer. And the square root of x squared plus 4. Okay. Now, let's do B, G composed of F. Okay, so um, I'm going to replace f of x with what it is. It's the square root of x plus 4. And I'm going to evaluate it to function g. So everywhere I see x, I'm going to plug in this square root of x plus 4. And there's only one x, so we have this, right? We have the square root of x plus 4 squared. Okay, so when I do this, um, the square root with the square, again, you guys like to say it cancels, but it becomes an exponent of 1 for the x plus 4, giving me just x plus 4. Okay. Now, we want to, so that's my answer. So we want to review the domain because this is very useful for your homework. So they're going to ask you also for the domain of these composite functions. Okay, so for instance, on this first one here, if I do the domain of f, okay, the domain of f is the square root of x plus 4. I need to find values that will give me an error inside, right? We don't want to, for when dealing with square roots, we don't want to have a negative value in here. So here we see that if um, x is greater than or equal to -4, we can use, right? Anything to the left of x, we wouldn't be able to use from -4, because if we use -5 plus 4 would give us a -1. So x has to be greater than or equal to -4. So my domain, all the values that I can use are starting from -4. And you see, because I can use -4, -4 plus 4 is 0. The square root of 0 is 0. I have a bracket now. So it's bracket -4 all the way up to positive infinity. So this is my domain for the function f. But I also have to check my domain of g. Before I can state the domain of the composite function, I need to check both functions individually. Okay, so here my domain of g is, since I have an x squared, and we covered this function is neither a fraction, is neither a square root, or a log. So hence the domain is all real numbers. Okay, so when they're asking us to find the domain of f composed of g, okay, we notice that no matter what we get, the domain will have always a negative infinity to positive infinity for my um, square here. Yes? So when considering the domain of G, which is from negative infinity to positive infinity, what has in common from steps 1 and 2? Well, both of them have in common the negative infinity to positive infinity. So hence the domain of f composed of G is from negative infinity to positive infinity. Okay, they have to both have it in common in order for this to be the domain. So let's go ahead and look at B so you can see so we can practice. So here on in the x plus 4, here we have, again, from negative infinity to positive infinity. But when we're dealing with the domain of the square root here, we had a condition where we had from -4 to infinity. So here we have a different um, oops, we have a different domain. Okay, so when they're asking us on 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 some of these, if they don't match, for instance, the answer would be the one with the most restriction. Okay, so the answer would be from -4 to infinity. Okay, keep that in mind. All right, so let's practice some more, and then we'll practice some more domain questions. So we have f composed of g and g composed of f. So let's go ahead and have f of x, which is 1 over x. G of x is x plus 2. So let's do f composed of g. So again, we want to evaluate f of g of x. Replace g of x with what it is. It's x plus 2. And everywhere I see x for function f, I'm going to plug in this x plus 2. So we have 1 over x plus 2. There's nothing for me to simplify, so that is my answer. Okay, 1 over x plus 2. Let's go ahead and do B. G composed of f. So G evaluated for the f of x. Replace f of x with what it is. F of x is 1 over x. That means that everywhere I see x for function g, I'm going to put in 1 over x. So this is going to give me 1 over x plus 2. There's nothing for me to simplify, so my answer is going to be 1 over x plus 2. Okay? So let's go ahead and look again at the domain. Okay, so let's look at the domain of 1 over x. So the domain for this function, it's clearly, hopefully we see that I cannot use 0 on the denominator. So my domain is from negative infinity to 0 and from 0 to positive infinity. Okay, now what is the domain for x plus 2? So my domain for x plus 2, again, that is neither a fraction or a square root or a log. So my domain is from negative infinity to positive infinity. Okay, right. So if we look at here on our second one, our domain for f dot g, we have we cannot use negative 2. So my domain for the 1 over x plus 2 is from negative infinity to negative 2 and from negative 2 to infinity. Now, if I'm considering the domain of g by itself, again, this one had no restrictions, so it's negative infinity to positive infinity. So since this one doesn't have anything in common, the domain of f composed of g is from negative infinity to negative 2 and from negative 2 to infinity. Okay, so again, since these two didn't have anything in common, it has to be the one with the most restrictions. This is my answer for the domain of f composed of g. Okay. All right, so let's go ahead and um, look at finding two functions f and g such that f composed of g equals h of x. Okay, so here we have h of x is equal to 3x plus 9 squared. So what they're asking us to do here is work backwards. They gave us the composite function, and what we want to do is we want to separate it into two individual functions, right? So we want to get f and g. Okay, so the way I like to do it is just like starting out with what's outside the parentheses. So outside the parentheses, I have a squared. So that means that since f was first, the function for f would be, again, this is what I'm talking about, f of x, what is inside the parentheses, and g of x would be anything that's outside the parentheses. Oh, excuse me, inside the parentheses. I think these are backwards. So again, the way I would do it is g of x is outside the parentheses. So we have here, this is correct. The function here is x squared, and I think these are backwards. I think it should be the other way. F should be um, x squared, and g of x should be the 3x plus 9. Okay, so let me see here. Oh, yeah, see, now it's correct. This syntax, what the way it was doing it, it was correct. Um, the problem is asking f dot g, but what we were really solving is g of x. This is correct. G is my function, x squared in this case, and f is the input, the 3x plus 9. This one, it is correct. Okay? So there was a typo there. All right, how about this one? F composed of g of x, and we want to find out h of x. So h of x is the square root of 2x minus x. So again, what I like to see here is what's outside the 2 minus x. I have a square root. So what f should be the square root of x. Okay, so which is, this one's correct. What is the square root? And g of x is what's inside. Yes, so here f of x, I'm doing it again. So 2 minus x. Let me ask, Ms. Chuka, this is correct, right? The way they're labeling these are not correct?
So usually one of the things I tell my students is pick one of the functions to be the inside and one to be the outside, and then check to see if you were to do the composition, does it come out as h of x? If not, then just reverse them. So in this
Oh,
case,
okay.
g of
I
x,
get you.
and so that's probably what happened when we were doing the PowerPoint is we were guessing which was the inside and the outside. But in this case, g of x is going to be what you want to put on the outside function, right? So they're reversed again here. But if you continue, we'll see how it's fixed.
Excellent. Okay, that makes sense. So we were doing trial and errors. Okay, I was just wanting to go straight to the answer. Okay, so again, so as Ms. Chuka mentioned, sometimes we don't see it, so we're just picking, right? And we want to see that what we picked, it makes sense, right? So here, again, it resulted that we didn't choose correctly. Um, when we were evaluating this, if we were evaluating this, what we are finding out is that what we're really doing is G composed of F, right? So then to fix it again, if they're asking us to find F composed of G, we know that we have to switch them, yes? Okay, all right, let's go to this next example. It says determine the open intervals on which the function is increasing, decreasing, or constant. Enter using interval notation. If an answer does not exist, enter DNE. Okay, this is awesome. Okay, so what they're asking us is to evaluate graphs now. And again, the thing we need to know is when we're reading graphs or evaluating graphs, we read graphs just the same way we read our textbooks from left to right. Okay, so in this particular problem, they gave us a function. The function is x squared minus 12x, and they gave us a graph, which is great. So what this means is, let's do the first one, increasing. We want to find out where the graph, if we're reading it from left to right, where the graph is increasing in value, right? And the book likes to say, when you pick a x1 point and an x2 point, the x1 point is smaller than the x2 point, right? So if you see here, starting here from 6 to infinity, the graph is going up, 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 right? So the interval of where my graph is increasing, again, is starting from 6 um, and it's going to ever for the right. But here, let's go ahead and explain it with the decreasing. Okay, so again, we're reading the graphs from left to right. If we here see from negative infinity, the graph is going down, 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 down. So that means that it's decreasing. And here at this point again that I mentioned to you at 6, we stop. We stop going down, and then we change to going up, right? So um, we have some funny little pictures here. Okay, so then here from 6 to infinity, you see that our graph is increasing and it's in blue, right? So do you see any that is constant? And then when we're talking about constant, that means think about an EKG meter, right? Where it goes flat line. Hopefully we never get to see that, but right, what that means is it's a horizontal line. It's not neither going up or going down. And that's what constant means, that the graph is neither increasing or decreasing, and we don't have that here. So there's not a situation where the graph is constant. So now we can go ahead and answer our question. So if you see here, the one in green are showing us all the places for x where it was decreasing, and the one in purple is showing all of the values for x where it was increasing. Okay, so we want to write these in interval notation. So again, increasing is from 6 to infinity. And I want to point out something which to help you. I know that the computer said interval notation, and if I were to do this in interval notation, this 6 should have had a bracket, okay? But the computer, since we're just talking about increasing and decreasing, and it just go ahead and put parentheses to all of them. Don't worry about the brackets, okay? Um, it's just the way they set up the system for the increasing, decreasing evaluations. So again, on this one, just use parentheses on all of them. So it's increasing from 6 all the way to the right to positive infinity. decreasing from the left, from negative infinity all the way up to 6, and then stopping at 6. And again, there was no situation where I had a horizontal line or a flat line. So there's none that are constant. So you're going to put on your computer D&E does not exist. Okay. All right. Let's see. Do we have more? I think I'm going too fast. All right. Let's look at this one. Determine the open intervals in which the function is increasing, decreasing, or constant. Enter using interval notation. If the answer does not exist, enter DNE. DNE again means that it does not exist. Okay? All right, so someone's helping me out with putting the arrows. So even though you might not see arrows on the computer, um, if they didn't put a fill circle, like a heavy dot, like how you see here on the bottom, or an open circle, that means that the line is going forever to the left, and here the line, and on the other side, the that line is going forever to the right. Okay, so again, we're reading from left to right. So if we want to do where the first one, maybe that's the first one that we're doing, or we can do both of them at the same time. Okay, so if we're reading the graph from left to right, from negative infinity, I am decreasing here. I'm going down, 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 down until I hit, you know, x equals -5, right? And then I stop. Okay, and then the graph picks up again over here at +5, and then the graph is increasing, going forever up, right? So now I can answer this question. Where is it increasing? So starting at the x value 5 all the way up to infinity forever. So it's from 5 to infinity. Where is it decreasing? From negative infinity all the way up to when I reach x equals -5. So that's where it stops. So that is my interval. And again, on this particular one, there isn't a situation where we had a flat line. And again, just to show you what I mean, if this graph would have had something like over here, just a horizontal line, then here is where I would put that I had a constant. And let's say that it was here, and let's say that this value that is pointing was, let's say 11. Okay, so for the answer for constant, the way that I would write is, again, I would have put a bracket, but it would be from 11 is the x value where it starts being flat. And I can see that since they didn't put an arrow, I know that this graph is going forever to the right. So it would be to positive infinity. Okay. So this is evaluating functions and determining the intervals in which a graph is increasing, decreasing, or constant. I think I finished a little bit early. Miss Chuka, do you have anything that you would like to add?
Yeah, since we finished a little bit early, let me go ahead and just do maybe one or two examples on inverse. Go ahead and just do maybe one or two examples on inverse functions, which is from section 1.9 that is supposed to be this week, and then we can go from there. So in section 1.9, they're going to ask you to find the inverse of a function. And so the inverse of a function, the symbol that we use is f and then a power of -1. So anytime you see this, they're talking about the inverse. There is a test to determine if a function has an inverse, and we call it a horizontal line test. In earlier sections, you used a vertical line test to determine if something was a function. So in a little bit, we'll do that. We'll do an example on that. So here it says use the table of values for y equals f of x to complete a table for y equals f of the inverse. And so what you want to do here is basically when you're looking at inverses, whatever is in the domain, which is your x's here, in the inverse, they become the range, and the range becomes the domain. So what we can do here, our solution is going to be us switching these values. And so we would have our x's are now the y's that we had here become the x's, and then the x's that we had up here become the y's. Okay, and so since we always want to list the smallest value first, um, we also made sure to do that as well. And so here it says, do the functions have an inverse? And so what we can do is apply the horizontal line test. And so if I draw a horizontal line, let me go back. If I draw a horizontal line here, let me get the pen out. So if I draw a horizontal line, notice that the line is going to touch in two locations. And so since it does that, the graph touches here and it touches here, the horizontal line. Therefore, it's not going to be a one-to-one, or it's not going to have an inverse function. If we look at the second one, if you draw a horizontal line, then it's only going to touch in one location. And so that's going to make it have an inverse. Now, one of the things that you want to do is figure out if something has an inverse. Let me go ahead and go to a different problem really quick. Just for time, if we have time, we'll come back to this one. So what you're going to need to do is you're going to want to find if something has an, or you're going to want to find the inverse. And so this is a question that I wanted to work out with you. So it says here, if you want to find out if this has an inverse, if you want to find the inverse, then these are the steps that we're going to take. So the first thing is to determine if the function actually has an inverse. Since this is a line, then it's going to pass the horizontal line test. Now that we know it has an inverse, the first thing you want to do is change f of x to y. So I'm going to have y is equal to f of 5x plus 9. Then we're going to switch the x and the y. So instead of y, I'm going to have x. Instead of x, I'm going to have 5y. Then the next step is to solve for y. So we're going to subtract 9, and then I'm going to divide by 5. So now I have x minus 9 divided by 5 is equal to y. So our last step is to replace y with our symbol f of negative 1 of x. So this result is going to be your inverse. Okay, so that's going to be your inverse. And we can try another one here. So if you want to find the inverse, first you want to make sure that this function will have an inverse. Well, the x plus 6 squared, that one is a parabola, but they only want us to consider the domain from x greater than or equal to negative 6. So we're only going to be looking at part of a parabola. And so that's going to be okay. It's going to pass the vertical line test. Okay, so the first thing you want to do is change f of x to y. And then we have x plus 6 squared. Then we're going to switch the x's and y's. So here's my y. So now I have x. Here's an x. So now I have a y. And then we need to solve for y. So to solve for y, I'm going to take the square root on both sides. And the square root and the power of 2 become a 1. Or like some people like to say, they cancel out. So we get y plus 6 is equal to square root of 6, square root of x. Subtract the 6. And so this is going to be what we have left. And the last step is change your y to f inverse of x. And so our result here is f inverse of x is equal to the square root of x minus 6. Okay, and so that was just a quick way to figure out how to find the inverse. Okay, and so if I go back to the beginning, the one that I skipped, just really quick. It was this one. So if you want to know if these are inverses of each other, then one of the things that we can do is what Mr. Carizales covered earlier. So it says if two functions are inverses of each other, then the composite of these functions will have to be equal to x, and g composed of f is also going to have to be equal to x. So what we can do is figure out what f of g of x is. And so let's do that first. So here I have f of g of x. G of x is x squared minus 4, so I plug that in here. And now I'm going to take whatever I have inside of this parentheses and plug it in for x in the function f. And so we get x squared minus 4 plus 4. Simplify. Negative 4 plus 4 is 0, so we're left with x squared. The square root and the power of 2 gives us just x. So that meets the first condition, but it also has to meet the second condition, which is what happens if you do them reverse. So here we have g composed of f of x. So I'm going to substitute f of x, which is square root of x plus 4. Whatever I have here, I'm going to plug it in for x. So let's go ahead and do that. So I have square root of x plus 4 squared minus 4. So the square root and the square become 1, or they cancel out. So we get x plus 4 minus 4, and that's also going to give me x. And just so that you have a visual, the graphs here, this is the square root of x plus 4, and here you have your x squared minus 4. Let's see, okay. And so for the x squared minus 4, they only want us to consider the x is greater than or equal to 0. And so that's why when you had the whole parabola, if we only looking at this part of the domain, now we're just going to concentrate on this piece of the graph. Okay, so if I put them together into one xy coordinated plane, then the graphs look like this. Okay, and if these graphs are inverses of each other, then they're going to reflect on this line y equals x. And so whatever is on this side reflects on whatever is on this side. So that's one way to tell if you have inverses using the graphs. And I believe that was it. I might have gone a little too fast, but if you want to download this presentation, you should see a box with an arrow pointing down right about here, right on top of this pointer. You click that, it's going to help you, it's going to allow you to download the presentation. And so that is it for today. So we do thank you for coming, and they're going to go ahead and share with you what we're going to be covering next week.
Thank you, Ms. Chuka, and thank you also to Mr. Carizales um, for the wonderful presentation. Um, for the wonderful presentation. If you, like Ms. Chuka said, if you want to download the copy of the presentation, you can go to the right corner. Let me see if I can get that little arrow. There it is. To the right corner, and then click on the box with the arrow going down, and you'll be able to have that. We do want to remind you all about our previous recorded sessions, which are available on YouTube on the Tejano Virtual Event playlist. This session will also be available on that playlist later today. Also, linked is a short survey to help us improve our Tejano virtual event sessions. Please take a few moments to fill out that survey. Before you all leave, I want to share the Tejano virtual events flyer with the sessions that we will be having next week. At 1 p.m. today, we will be having the distance learning with Luz Cadena. We're also going to be back with Happy Math Hour next week at 11, where we're going to be covering the final exam reviews for the Math 1314 and also for the Math 1324. At 1 p.m. session next week, we're going to be covering the EPCC Mental Health Committee presenting on self-care. Thank you all for coming in today. We hope you all have a lovely weekend. And if you have any questions, please feel free to use the chat box or your mic. And we hope to see you again for the Happy Math Hour. Bye-bye, everyone.